So we have seen an example of what I have called following the trace of execution, where we look at the code and try to see how many times every instruction is run, and then we relate that to the complexity, the size of the data, to derive the complexity of the algorithm. We saw a loop that was repeated n times when n was the size of the data, and it had constant time instructions inside of it. So all of that was, we said, big O of n. It was a linear time algorithm. And we are going to be continuing with this type of analysis for the rest of this session. But right now, let's have a look at the sometimes existing differences between this type of analysis of, let's say, more theoretical analysis and what we can see from the runtime of the algorithm. To do that, here we have this code cell, which I'm not going to run at this moment because it can take a while, but I very much encourage you to do that and to see exactly what's going on. It's good coding practice. But basically what I'm doing here is I'm putting some data, making some random lists, and then searching in this random list using the traversal algorithm, and also using a simple search loop, not the traversal algorithm, a simple search loop, and then also using a dictionary. Okay, so I'm searching for something, basically using a search loop in list, which we saw was linear, and also using the search function on a dictionary, which I'm going to be saying a little bit more about in a second. My point here, the important point here, is that when I plot those things, the list search and the dictionary search, they don't have a very clear tendency, even when I plot them together. We can see that the time it takes to search in a list grows when the size of the list grows, and the time it takes to search in a dictionary doesn't seem to grow when the size of the list grows. Okay, but the tendency for the searching time on the list is not clear. We had seen in the previous session, that the time it takes to search in a list is linear. We spoke about worst case complexity, and I heartily recommend that you have a look at it here again. Okay, but the tendency is not that clear. Is this a linear tendency? Well, I'm not sure. It has lots and lots of ups and downs. Okay. Basically, what is happening here is that the size of the data that I'm considering is small, and I cannot see the tendency very well. Okay, so even though the time plots give me some information, sometimes they are not super helpful when it comes to telling the long-term tendency of an algorithm. Sometimes I want to compare more than one algorithm, and one of them is much bigger than the other, so I cannot see very well the tendency of the smaller one. Sometimes I would need much longer data to see the tendency of a particular algorithm. To make this even clearer, what we are going to do here is that we are going to repeat the search, this linear search that we had been doing using a loop. Okay, so we change for a number of repetitions that make me do this search inside of my list quite a lot of times. Okay, basically I have here what I used to have, the usual search loop, and I have a new for loop here that makes me repeat everything r times. So I'm just doing what I was doing, but I'm repeating it a lot of times. And when I plot that, the linear tendency is now much, much clearer. So I always need the two things. I need the theoretical analysis to, let's say, prove and have a very strong indication of the time it takes to compute my algorithm, and then I can plot things, but I have to be a little bit careful just looking at the computation times. They do help to make sure that I wasn't wrong, but sometimes the size of data that I consider is important, and sometimes comparing two algorithms is not straightforward in terms of plotting them. Regarding the search in the dictionary, we saw before that it didn't grow too much. Okay, it appeared to be small. We are going to see this later in more detail, but I just want to say here that if everything goes well, and that has to do with something called hash functions, and I again recommend that you read this with some detail, but basically if the dictionary where I have stored my data is working well, and what that means is what I want you to read about, searching inside of a dictionary is also constant time. Okay, so the behavior that I saw before, where the computation time does not really grow when the size of my data grows, is actually what is expected to happen if my dictionary is working properly. The time to search in a dictionary as the time to access a list is constant. To be fully precise, and this is also an important concept, this is an amortized constant time, which means that when I build a dictionary, I need some time to set up everything. So if I only do one element search inside of a dictionary, that might take some time. That might lead me to think that things are not constant time in total. But if I do subsequent searches, if I do more than one search, in particular if I do n searches, then the total time of the n searches is n. And because of that, because if n searches take n time, what it means is that each of them takes constant time, O1. What I'm saying here is the amortized time, the time divided between all my searches, is actually constant. That's a bit of a deeper complexity concept, amortized time, which we are only going to be seeing in terms of dictionaries, but that is pretty important in practice when using different data structures, and this is something that makes dictionaries very, very popular.